300G maneuver would instantly perish. His internal organs would continue moving forward and crush against the skeleton.
If they were similar to us, they'd probably have to have a way of injecting fluid, internal fluid, inside their bodies so that they dealt with this problem of their organs floating around inside. And if they were strapped in properly and cushioned properly, end up not having internal damage when they accelerated and decelerated.
To effectively cancel the inertial effects on the craft itself, the pilots might switch on a technology that is beyond the reach of modern humans.
So in order to cancel out the effects of a 300G turn and not be squished by that amount of force, you'd have to have some sort of technology or a device that was capable of canceling the effects of inertia.
The device would have to manipulate the force of gravity, using a type of force field to counteract the gravitational forces that rule the entire universe.
This device you could turn on if you wanted to, then turn it off if you wanted to, or maybe it would come on and off automatically. This is high technology that's out of sight.
But if science can't yet explain how these craft could overcome the deadly problem of inertia, can it help explain their shapes? Particularly the most famous shape of all, the flying saucer. In the late 1950s, the U.S. Air Force tested the Avro car, but the design had poor stability and few aerodynamic advantages, proving that high speeds are unattainable for saucer craft in Earth's atmosphere. The delta wing, or wedge shape, is a far stronger candidate, a fact that is well known by modern military aircraft designers. In fact, the percentage of UFO sightings reporting a wedge-shaped craft have increased in recent decades, a trend that mirrors the emergence of swept-wing jets and even flying wing designs, like the B-2 stealth bomber.
The shapes that people have reported over the years have changed, with the most recent ones being more wedge-shaped. So really, people's accounts tend to reflect the most advanced aircraft of the time.
Beyond movement and shape, any attempt to explain the science of UFOs has to deal with the noise factor, or rather, the lack of noise. UFO reports consistently claim that the objects move without making any sound.
Almost all of these sightings, it's a real rule, there's no noise, which you would expect to hear from any fast-moving craft in the Earth's atmosphere. You would hear it.
What actually happens is that you get what's called a sonic boom, and that's a special pressure wave that sweeps through the atmosphere along with the craft. So you're on the ground, and that huge sonic boom is a result of that pressure difference between the front of the aircraft and the back of the aircraft as it pushes through the atmosphere.
Could an alien craft somehow cancel out the enormous pressure wave that supersonic flight generates? The answer could lie in the technology used in the latest generation of digital noise-canceling headphones.
So there is such a thing as a sound-canceling technology where you take a particular sound that you're interested in canceling and kind of broadcast the negative of that sound to cancel it out. Now, I'm not aware of any technology that's capable of doing that with shockwaves.
Canceling out the ear-splitting, body-shaking effect of a sonic boom would certainly require some advanced engineering skills. And if there is silence, what about invisibility? Some reports claim that UFOs simply disappear into thin air. One promising human technology currently being researched might explain such phenomenon.
There is a technology on the horizon which might change things visually, and that is a kind of light-bending technology. As a class, they're called metamaterials. If you want to think about popular movies, think the invisibility cloak in the Harry Potter movies.
Metamaterials use combinations of polymer substrates, gold, and copper to forcibly bend electromagnetic waves around an object. The light is guided around the object, rather than being reflected or refracted. But advanced materials, stealth capability, and mind-bending maneuverability would all come to nothing if our visitors were unable to get to Earth in the first place.
I'd say that the chances of another civilization making it here to visit us are pretty minuscule, but if they did make it, it would mean that they had solved a whole bunch of problems, including material science problems that we don't have answers to. So they'd have technology far beyond ours, perhaps even beyond what we've dreamt of at this point.
But scientists can imagine several ingenious technologies that could bridge the seemingly unbridgeable distance between the stars, including one explosive propulsion source that's so apocalyptic we might see them coming light years away. For decades, countless UFO reports have surfaced from cities and countries around the globe. But not all UFO sightings have been reported from the surface of planet Earth. On July 19, 2009, viewers of a NASA video feed from the Space Shuttle Endeavour reported seeing a disc-shaped object hovering above the shuttle's mechanical arm. Space-based UFO sightings like this have purportedly happened throughout the history of manned spaceflight. Unspecified cosmic phenomenon? Or could it suggest the possibility that huge extraterrestrial starships are cruising the Milky Way galaxy?
Space travel between the stars, it's a staple of science fiction, right? You see it every night on television, you see it in the movies all the time. But could we really do it, or could any species really do it? Well, the distances between the stars are enormous, really enormous. Interstellar travel doesn't violate physics. It isn't that you can rule it out and say, there's absolutely no way they can come here. It's just that it's very, very hard.
Just traveling from the Earth to Alpha Centauri, our closest neighboring star at nearly 4.5 light years, is beyond the reach of our most powerful rockets.
If an advanced civilization were to visit us from a distant star system, we can pretty much rule out that they would use chemical rockets to get here. Despite the impressive pillar of fire and smoke that we see during Apollo, Saturn V, or shuttle launches, chemical rockets don't get you very far in the solar system.
To give you some context for that distance, our furthest known space probe is Voyager 1, launched in 1977. It's been flying for 34 years at 38,000 miles per hour, and it's only now starting to leave our solar system.
If its destination were Alpha Centauri, it would take over 56,000 years to reach even the closest star system. To engage in interstellar missions on timeframes of a human lifetime, around about 50 years, we can see that we need to increase the speed that we can travel by at least a factor of 1,000.
Scientists have determined that the speed of light is a mind-blowing 186,000 miles per second. A spacecraft traveling the star system would have to reach a significant percentage of that speed, even to reach the nearest star. The biggest obstacle is weight. A chemical rocket exacts a huge weight penalty because its entire fuel supply must be carried on board.
We can calculate that even to reach 6% of the speed of light using chemical rocket fuel, you would need more rocket fuel than exists mass in the universe. So we really know that it's actually impossible to reach another star system using chemical rocket fuel.
If extraterrestrial visitations are even possible, their spacecraft must solve this problem. In 2011, NASA's NanoSail D became the first solar sail to orbit the Earth. The ultra-thin 100-square-foot sail uses sunlight, or photon pressure, as a source of propulsion.
One of the immutable limitations of rocket propulsion is the fact that any rocket has to carry its fuel with it. A solar sail can take advantage of the naturally occurring resources, namely photons emanating from the sun, which can be used to propel that solar sail. Similarly, a hang glider can fly without any fuel or an engine just by taking advantage of the natural resources we're surrounded by, namely the atmosphere and the laws of aerodynamics.
To achieve sufficient speeds to tow a spacecraft supporting life forms, the sail would have to be huge, up to hundreds of miles in diameter. And because the photon pressure from a star would decrease the further the sail traveled, some have envisioned a concentrated laser beam directing energy at the sail.
Eventually, and sadly, this hang glider and all hang gliders at some point have to land. But a solar sail riding a beam of laser energy could conceivably travel to the stars.
The max speed of a solar sail? About 10% the speed of light. Travel from Earth to Alpha Centauri using laser-generated photons? About 45 years. Currently, NASA and other space agencies have plans for launching more solar sails. But there are other, more powerful sources of propulsion in the universe.
In the 1960s, a method of propulsion was proposed where a spacecraft would literally drop a series of explosive charges out the back, and the force of the explosions would push the spacecraft forward. The prototype was called the Orion drive, and there were actually a series of experiments done with conventional charges to show that it would work. The Orion drive, however, was proposed to use nuclear charges. In order to simulate an Orion-style propulsion system, Paul and Jim here are rigging up a demonstration where they're going to put a small chemical charge inside this barrel, and we're going to lift this off the ground 50, 60 feet in the air. We're going to actually calculate the energy released in this explosion and compare it to a nuclear charge you might find on an actual Orion spacecraft system. Our Orion spacecraft simulator is rigged and ready to go. We're going to light off the charges inside, blow the can up into the air, and compare that with the energy released from a typical nuclear explosion that would be used on an Orion-style drive.
The Orion spacecraft, studied at Los Alamos in the late 1950s, proposed nuclear fission as its propulsion source. Fission energy is produced when the nucleus of an atom splits into smaller parts, producing free neutrons and protons that release tremendous gamma-ray energy.
The explosive charge in this 35-pound barrel lofted at about 60 feet in the air. A small nuclear charge in the Hiroshima range would liberate about 27 million times more energy. Clearly, that's a practical propulsion drive for interplanetary or even interstellar travel. Because of the huge explosions that an Orion drive would require, on the back of the spacecraft you would have a huge thick metal plate that would absorb the thrust of the explosion and a series of shock absorbers to keep the crew from getting jolted each time the charges went off.
The max speed of a nuclear-powered fission spacecraft? About 5% the speed of light. Travel time from Earth to Alpha Centauri? About 90 years. Despite its powerful fuel source, the fission craft is actually slower than a solar sail. Boosting speed would mean turning to another, more intense nuclear reaction.
Fission technology is well known and understood, and we've been using it to generate power here on Earth for decades. But there's another kind of nuclear technology, and that's nuclear fusion.
Fusion is the power source of the sun. In the core of our sun, the temperatures are so high, atoms are moving so fast that they slam into each other, creating new elements and liberating energy.
The opposite of fission, Fusion energy is produced when two atomic nuclei fuse together to form a single heavier nucleus. The result is a huge liberation of energy. A fusion-powered spacecraft was proposed in a 1970s study called Project Daedalus. Its mission called for a trip to Barnard's star, some 5.9 light-years distant. Instead of nuclear bombs, the fusion-powered craft creates the propulsion on board in a reaction chamber.
The fuel pellets for the Daedalus-class starship consisted of pellets composed of a deuterium-helium-3 mix. These would have been ignited by what we call relativistic electron beams. These are extremely high-energy electrons that would have hit the deuterium-helium-3 pellets, caused them to fuse, and a huge amount of energy would be released. The Daedalus design called for 250 of these pellets to be released every second for over 2 years. The spacecraft would have weighed 55,000 tons, most of which would have been fuel.
The weight penalty for such a spacecraft would be high, but an advanced civilization could eliminate the problem by mining the hydrogen fuel during its interstellar journey. Deuterium, or heavy hydrogen, exists in abundance on Earth, notably in seawater. But helium-3 is a much rarer isotope. In our solar system, it can be found on the Moon, and in vast quantities on Jupiter and Saturn. Scientists have proposed using huge hydrogen scoops to mine the helium-3 needed to cross the void of space.
So it's conceivable that if you had a craft that was powered by nuclear fusion, you could go to another star system and then use the hydrogen available from that star to refuel.
The self-contained, fusion-powered spacecraft could avoid a huge weight penalty and reach speeds that could allow near-star exploration in a reasonable time frame. The max speed of a nuclear-powered fusion spacecraft? Up to 15% the speed of light. Travel time from Earth to Alpha Centauri? About 35 years. The immense costs, the logistics, and even the politics of nuclear-powered spaceflight long ago caused humanity to scrap any and all plans. But a sufficiently advanced society could trade nuclear propulsion for what seems like an impossible paradox, traveling at light speed without moving at all. Can UFOs actually achieve the immense speeds required for interstellar travel? One potential answer may be buried 30 feet beneath the ground in America's heartland. The Fermilab Tevatron Collider, outside Chicago, Illinois. Racing just below the speed of light, particles of protons and antiprotons are launched in opposing directions. They meet in a high-energy collision. The impact produces gamma rays, the highest energy source known in the universe, and potentially the key to interstellar travel.
The best way of making antimatter here on Earth is to employ probably the most famous equation that Einstein taught us, which is E = mc squared, which tells us that for a certain amount of matter we can get energy. It's a great idea because it's incredibly efficient. You essentially take all of the mass in those particles and convert it into energy.
But how can antimatter exist in the universe if it must be artificially manufactured? That's the question that Stephen H. from Philadelphia texted the universe.
Stephen, antimatter definitely exists, and when it meets up with normal matter, it explodes in a burst of electromagnetic radiation. Now, we can make small bits of antimatter in laboratories, but we can also collect antimatter from space. Some cosmic rays, which are charged, very energetic particles coming from space, actually consist of antimatter.
Currently, the super collider is the only practical way to produce antimatter. And right now, it's created in very small quantities.
If we could figure out a way to both create and store enough antimatter, we would have a storable fuel which, when mixed with ordinary matter, would liberate a huge amount of energy at a rate way beyond what either fission or fusion can do.
Because we know antimatter exists, and we know antimatter can be created and stored, it is conceivable that an advanced civilization could create and harness the power of antimatter in sufficient quantities to create an antimatter rocket.
An antimatter ship could achieve unbelievable velocities, cruising just below light speed, nearly matching the speed of a starbeam streaking across the galaxy. Travel time from Earth to Alpha Centauri, 4.5 light years distant, about 5 years. In human terms, the cost of creating enough antimatter particles to power such a starship would be astronomical. It might be affordable in alien currency, but an antimatter spacecraft like this comes at a high price. The gamma rays from antimatter propulsion are so dangerous, they could destroy the cell structure of any living beings aboard ship. This starship would have to include an advanced shielding mechanism to keep the crew alive. And at such high rates of speed, there are equally destructive threats in the universe.
Space is pretty empty, but if you were moving close to the speed of light, you'd need an extremely effective shielding system that would allow you to be protected from interstellar dust particles that would all but annihilate a spacecraft traveling that fast.
But if space debris is so dangerous, why not avoid it completely? The solution might be one familiar to Star Trek fans, namely a starship that could achieve light speed without even moving.
In effect, one would create what is called a warp bubble, the name taken straight out of science fiction, and that would involve compressing a region of space-time in front of a spacecraft and expanding a region of space-time behind a spacecraft, while the spacecraft itself sat stationary inside this flat bubble. And one would effectively be riding a wave of space-time.
A warp drive may seem like pure sci-fi fantasy. But in 1994, a well-respected young physicist named Miguel Alcubierre published a serious proposal outlining how to travel in a controllable space warp. There are huge obstacles to Alcubierre's warp drive solution. The biggest is called dark energy, a cosmic phenomenon recognized in 2011 when 3 scientists were awarded the Nobel Prize for proving its existence.
The simplest explanation that's been proposed for the phenomenon of dark energy is that there's an intrinsic property of space itself that makes it want to expand. You can actually see it by looking at receding parts of the universe and seeing that there's this extra acceleration component, but it isn't a stored energy source like solar energy or other kinds of energy.
And so it's not inconceivable, it's not beyond the realms of possibility that some advanced civilization existing somewhere in the universe has learned how to harness dark energy to create an exotic form of propulsion.
But there's another obstacle to a workable warp drive. The only known way to pull a spacecraft forward within a warp requires harnessing the intense energy of a black hole.
The sort of simple notion is somehow to make a very concentrated bit of matter, extremely concentrated on the level which would cause a black hole. If you could generate a black hole on a small scale, so to speak, you could dangle it in front of the ship and use its space distortion to sort of drag the ship along.
And exactly how fast could a warp drive tow an extraterrestrial spacecraft?
The clear implication of Alcubierre's work was that it should be possible, if you can make his design of a warp drive, to achieve speeds almost any multiple of the speed of light.
Travel time from Earth to Alpha Centauri aboard a lightspeed craft powered by a space warp? About 4.5 years. Or less, as long as everyone on board doesn't incinerate.
One problem with the Alcubierre drive is within that warp bubble, temperatures would rise to far hotter than the core of our sun. That's hot.
Just one more small problem to solve for the chance to reach planet Earth. But what if such an alien spacecraft were to arrive in Earth's atmosphere, riding in a warp bubble, towed by a black hole? It might not be the first mass witness UFO sighting, but it would certainly be the last. March 13th, 1997. Thousands of people witness an optical phenomenon drifting across the Arizona skies. Reports of a series of bright lights in geometric patterns are widespread, including multiple sightings over Phoenix of a craft up to 1 mile wide with lights winking on and off in sequence.
Reconstructing the events of that evening, the lights of the Phoenix lights were almost certainly flares dropped by an Air Force A-10 aircraft in conjunction with the human tendency to envision a solid shape connecting them. That's the best explanation for the Phoenix lights.
For many, the Phoenix Lights incident was direct proof that a huge extraterrestrial craft had arrived. Some even called it a mothership. The purpose of an extraterrestrial mothership is fundamental to the theories of alien visitation. It's the only way to bridge the vast distances of interstellar space.
The term mothership, I think, came into being around the same time that flying saucers as a term came into being. And I think the universal notion was you couldn't make an interstellar trip in a person-sized craft. You had to have something really large.
An apt earthly analogy of a mothership is that of an aircraft carrier. An aircraft carrier travels the vast distances across the oceans, but its purpose is to transport smaller aircraft which can then go on and engage in whatever their missions may be.
If the journey to Earth is long, on the order of centuries or even millennia, the mothership would be much more than just an aircraft carrier.
There's the generational or arc ship, which is a very large spacecraft that is essentially an enclosed ecosystem in which generations of inhabitants expect to be born, grow old, and die over the long period it takes the spacecraft to reach its ultimate destination.
Perhaps with technology such as suspended animation, biological alien passengers could be put to sleep and revived after the vast journey. Surviving such a journey would also mean surviving the destructive energy powering the spacecraft itself. One logical design solution, a cigar-shaped mothership, is precisely what many UFO witnesses claim to have seen.
For any advanced propulsion system, you would want to situate the crew as far away as possible from the engine source. So one possible design would be a very long, thin design with the engine located at one end of the spacecraft and then some kind of truss connecting the crew section as far away as possible so as to avoid damage from high-energy neutrons, X-rays or gamma rays from the advanced propulsion system.
If such arc ships have in fact visited planet Earth, the evidence would be overwhelming and undeniable.
Something all these exotic and advanced propulsion technologies have in common is that they all radiate prodigious amounts of energy, and so we'd be able to see them like beacons on a lighthouse from sometimes light years away.
A concentrated emission of X-rays, gamma rays, or subatomic particles would be suspicious because we don't see that in our environment locally under any normal circumstances.
Beyond the obvious visual evidence, The physical effect of a mothership approaching so close to the Earth's surface could be a terrifying form of apocalypse.
If for whatever reason this extraterrestrial technology or civilization chose not to turn off their engines, it could be catastrophic for life on Earth, as we would be bathed in high-energy neutrons, X-rays, and gamma rays.
If it's something which is a version of a warp drive, then you're talking about space distortion. And you wouldn't want to be too close to any major mass, including a planet.
Such catastrophic visitations assume that aliens are willing to risk their own lives in interstellar space. But there might be a better way. They could stay at home and explore the cosmos using a race of thinking machines. For many ardent believers in the UFO phenomenon, the Roswell, New Mexico event in the summer of 1947 is the defining alien encounter in human history. In popular culture, the most lasting detail from the purported crash came from the descriptions of extraterrestrial bodies found at the scene. In the ensuing decades, this vision of alien beings, known as the Greys, became the accepted standard in science fiction and recurring alien encounter reports. The oversized heads may explain an expected feature in alien biology: greater intelligence. The larger skulls would contain larger, more advanced brains compared to ours. Mastering the profound challenges of interstellar travel would certainly require great intelligence. But might it require something that is beyond organic biology?
One area of science fiction where we might be making kind of a big mistake is to assume that the aliens are biological, that they're living things.
I think that the possibilities for the kinds of organisms which might travel between the stars are really wide open. And one possibility that has appeared on occasion in science fiction is machine intelligence.
According to a recent earthly equation, known as Moore's Law, the number of transistors on a single computer chip doubles every 18 months, meaning computer processing speed doubles. This trend has continued for more than half a century and is expected to continue through 2020 or later. The exponential explosion of processing speed is opening the door on a staple of science fiction called artificial intelligence.
So if you invent a thinking machine, 100 years later, that machine is not only smarter than you are, it's smarter than all humans that have ever lived. And that's the difference between artificial intelligence and real intelligence. Artificial intelligence can evolve enormously faster. But I think the form of AI that we find most both menacing and promising is the kind of AI that could, in fact, do what our brains can do, can think the way we can think.
At Stanford University's Artificial Intelligence Laboratory, the future of truly intelligent machines is rapidly approaching.
There are a few things that make AI difficult. One is we don't really know yet how to make computers learn as effectively as humans can. It seems that our computers today just aren't as fast as we would like them to yet to simulate the learning processes that take place in the human brain.
To demonstrate early-stage artificial intelligence, Stanford students designed a fighting robot, one that attempts to learn as it fights.
Okay, so what it's doing now, it's trying to defend itself. So it's reacting to your motion. So depending on how you move your sword, the robot will adapt to your motion and to your behavior.
How important a step on the road to true artificial intelligence are robots like this, Thorsten?
So here we are using artificial intelligence methods, like learning methods, to adapt to the environment of the robot. But we are still not at a stage where the robot is really thinking.
Today's computers are still far less intelligent than almost any human, but in the future, I think computers could eventually reach and maybe even surpass human intelligence. And if that's the case, imagine that each of us had a computer in our wallet, had a cell phone in our wallet that was as smart as Einstein or even smarter. How would civilization change, and what are the amazing things we could do then?
Advanced as it is on Earth, the fencing robot is but a crude analogy for the type of machine intelligence that could pilot an interstellar spacecraft. The immense obstacles of space travel, including the sheer timescale and cosmic hazards, build a strong case that a race of intelligent machines will make first contact.
But honestly, if interstellar travel really takes place, it seems sort of reasonable to not send the biological beings. I mean, they're fragile. They have finite lifetimes.
Just as NASA sends robotic probes to explore the solar system in advance of human explorers, our first contact with an alien civilization may be with its robotic probes.
Biologic being or AI super being? Our vision of an extraterrestrial will remain mere speculation until first contact is made. But how long will we wait? And despite a lack of hard evidence, just how likely is the existence of another intelligent civilization? Some believe it is highly likely that the universe teems with life.
The galaxy has been around for a long time. The solar system has been around for quite a long time, but the galaxy much longer. And the stars in it, many of them are much older than the sun and our solar system. So the chances are civilizations are out there. They've been around for longer than we have. If they exist, say, for 100,000 years, then the chances are pretty good, I think, they will have learned to either communicate across interstellar space or possibly travel.
Until first contact occurs, humanity will continue to scan the skies for UFOs. None have been proven to be extraterrestrial craft so far, but that does not rule out the possibility that humanity may one day discover evidence of an intelligent civilization, either in the far-flung heavens or much closer to home. In space, no one can hear you scream. As the promo line for Ridley Scott's science fiction film Alien, it was designed to send chills down your spine. It's based on the unsettling idea that space is a vacuum and sounds, whether screams, shouts, or songs, can't travel in a vacuum. But is that really true?
Well, it's kind of narrow to think that in space you can't hear anyone scream, because in fact, here on Earth, there are lots of sounds we can't hear. They're either too high a pitch or too low a pitch. Moreover, space isn't completely empty. And then finally, what's the definition of space? If I'm an astronaut on the surface of Mars and I have a spacesuit on, am I in space or am I not? Well, I would think I am.
Okay, let's try right over here.
Back on Earth, Bruce Betts of the Planetary Society in Pasadena, California, has given a lot of thought to Mars and the subject of sound. He's programmed his computer with what he calls the Marsinator to demonstrate what his voice would sound like in the cold carbon dioxide atmosphere of Mars without those spacesuits.
The atmosphere of Mars would actually change your voice so it sounded deeper. So let's go ahead and simulate that using the Marsinator. And I will record my voice, and then we will shift it to what it would sound like on Mars. This is what I'd sound like on Mars, although I'd be wishing I had some oxygen to breathe. Then I go ahead and process it, put it through the Marsinator, and then we play it back and see what it sounds like.
This is how I would sound on Mars, although I'd be wishing I had some oxygen to breathe.
Of course, if humans ever do make it to Mars, we will not hear their voices through the atmosphere. Instead, we'll get them via radio waves, the way many of our most important sounds already reach us.
Yes.
We're familiar with thinking of sound as something that comes through the air to us, just like we hear each other when we're talking. But in fact, a lot of the sounds that we hear are transmitted through electromagnetic signals. For example, your television actually transmits a television signal into sound that you can hear.
Who's our first contestant tonight?
Sound in the cosmos will never reach us directly across empty space. So radio, light, or other electromagnetic waves are the inevitable carriers, bringing us a universe we can hear in all its variety.
Space is actually kind of a noisy place. It has many, many sources of noise that we are able to detect with special radio telescopes, for example.
These alien sounds make up an incredible collection, the ultimate playlist. We've polled our expert panel of scientists, astronomers, and physicists to rank the top 10. The greatest sounds from the expanse of space, ending with a number 1 that will surprise us all. And now the countdown starts. Coming in at number 10, ringing out from a distance of 13 billion light years, the birth cry of the universe in a hit called The Audio Afterglow of the Big Bang.
It's remarkable that the young universe actually made a sound, and the reason we know that is that we can actually witness the glowing gases that were present at that time.
The glow from these gases is known as the cosmic microwave background radiation, or CMBR. It is a faint trace of microwaves that stretches across every point in the sky. Discovered by scientists in the mid-1960s, the radiation is the afterglow of the Big Bang. The famous blotchy satellite map of the CMBR represents the cosmos in its infancy, when it was only 380,000 years old.
When we look at the CMBR map, we're essentially looking at a voice print of the early universe, because those tiny variations in color correspond to variations in temperature, and those correspond to variations in density and pressure. Well, pressure waves are just sound waves, so we're seeing little variations in pressure, little sound waves in the early universe.
To understand the audio afterglow of the Big Bang, we need to know how the early universe varied its pressures to generate sound waves. To find out, astronomer Mark Whittle and organ builder Manuel Rosales visit the magnificent pipe organ at Claremont United Church of Christ in California. In a way, the 4,000 pipes in this organ are comparable to the voice of the early universe.
Manuel, the amazing thing about the early universe is that all its pipes were sounding together. And it'd be lovely if we could just try that with this organ. So do you think we could do that now, play all the notes at once?
Yes. Let's pull out all the stops and try it.
Ah, that's where that phrase comes from.
Yes.
Okay, let's go. Very powerful, but really hissy, white noise kind of sound. But an even more remarkable thing about the primordial sound is that, in fact, a few particular tones were present and were stronger at any given time.
This is the opening note of hit number 10, the audio afterglow of the Big Bang. A computer sound analyzer reveals its strong tones as distinct columns on a color-coded graph. As hissy as the early cosmic sound is, it differs from pure white noise, which has no organized features at all on the analyzer. The sound of the audio afterglow, on the other hand, comes through with a vaguely musical quality. The pipes of this or any organ are made of wood and metal, but the pipes of the early universe were pits of dark matter, the mysterious substance whose existence is known only from its gravity.
What drives the sound waves is gravity. So, for example, if there's a region of slightly higher density of dark matter, there's a gravitational force pulling in. Gas that's surrounding this region feels that pull and it falls in. But it's gas, so it also, as it falls in, it compresses. That compression acts like a spring, and so it pushes the gas back out. But then it overshoots until it falls back in again. And this is how the motion of the gas falls in, bounces out, falls in, bounces out. So we have an oscillating pressure wave, a sound wave.
The cosmic background radiation, as important as it is just a still picture. Its imprint of sound has the effect of no more than one noisy, barely musical note. And even hearing that is a struggle. The pipe organ helps show us why.
The sounds of the universe are way too low for us to hear. In fact, what's the lowest note that this organ plays?
It is a pipe 32 feet long, and it can only be played with one's foot.
Yeah, that's pretty deep. Well, 32 feet were nothing compared to the cosmic organ pipes. They were between 20,000 and 400,000 light years across.
Sorry, we don't have any pipes quite that long.
No.
The deep sound of the early universe is so low, we can hear it only after a massive shift upward. The background radiation of the universe dates from 380,000 years after its creation. But what happened before that? Is it possible to uncover the whole song of the universe from the very instant of the Big Bang? The cosmos is filled with a symphony of alien sounds, and we're counting down the top 10 of the universe's greatest hits. Number 10 on the playlist sings out with the earliest tones of the universe, from the audio afterglow of the Big Bang. But our download of the universe's birth song has some problems. With the cosmic organ playing all its pipes at once, what reaches our ears sounds like only one complex, noisy note. It's only one note because it comes from the pressure waves we read from the map of the cosmic background radiation, which is just a still picture of the sound in the early universe, taken 380,000 years after its birth. How then do we run the clock backwards and hear the rest of the song?
Modern cosmology is sufficiently advanced that it's possible to create a computer replication, a simulation of the young universe. It's possible to recreate within a computer what's going on and how the sound developed right from the very, very beginning through those first 400,000 years.
They are the same kind of supercomputer simulations that have given us pictures showing how the early universe evolved. The dark matter pipes of the early universe acted like those in the church organ. As bigger pipes were played, deeper notes were sounded. As the universe expanded, there was more space and more time. More space meant bigger pipes, so the notes in the song got lower and lower as the song played out. Put it all together, and the first 400,000 years of the universe can be condensed down to just 10 seconds. A haunting primal scream.
The gas that's falling in and out of these dark matter regions is ultimately going to become the first stars, the first galaxies, and ultimately it'll be corralled into the thousands of galaxies that we see around us today. So, while it's been amusing, really, and playful to reproduce these sounds for us to listen to, in the big picture, they play an enormously important role in crafting the structure of the universe that's going to unfold, and the universe that we find ourselves in today.
From the big band sound of the Big Bang, our countdown takes a step down in size to the modest 15 million light-year span of a galaxy cluster. Coming in at number 9 on our list of the universe's top 10 hits is The Deep Tone of Perseus. This is low sound to the extreme, emanating from the Perseus cluster, a grouping of roughly 1,000 galaxies, 250 million light-years from Earth.
The central galaxy in this cluster of galaxies has a huge supermassive black hole at its center.
The cluster's central galaxy is called Perseus A, and its supermassive black hole gives it what's called an active galactic nucleus, which shoots out energy in the form of gigantic jets, tearing into the surrounding space.
For reasons which we don't fully understand, it seems to be coming out, the energy is being produced episodically, about every 10 million years or so.
Those energy pulses are actually waves of pressure, and that's exactly what sound waves are. Pressure waves. The wave, as demonstrated by sports fans, has an up and down motion that's very familiar to us. But these UC Berkeley students will switch gears and show us how a sound wave is different.
Okay, everyone, lose the pom-poms. Since sound waves are pressure waves, we're going to build a pressure wave out of all these students. Okay, everybody, let's line up. You go over here and then shoulder to shoulder, just like this. Stretch out over there a little bit. No gaps. You're going to be students colliding with each other like molecules colliding in a sound wave. That's looking a lot better. Do you feel like a bunch of molecules? Okay, this is looking good.
We have a bass drum at each end of the line. You'll see why in a minute. We'll get things going with this drummer over here. He's going to hit the drum and watch what happens. In this case, the pressure is a good, healthy shove, and it moves from student to student all the way down the line. At the end, the last student applies his pressure to the second drum by banging on it. The second drum is like our eardrum. When pressure from a sound wave in the air hits our eardrums, we hear the sound. This is just how sound travels through the air, except instead of having students shoving each other, there are air molecules shoving each other. A sound needs a medium to travel through. It can't travel through a vacuum. So in fact, to get from point A to point B, you need air molecules hitting each other. That's how it works.
So how do those pressure waves from number 9's deep tones of Perseus travel through what's essentially the vacuum of intergalactic space? Astrophysicist Richard Pogge of Ohio State University gives us a sense of the emptiness in deep space at his school's football stadium.
Well, it's true that sound waves can't travel through the vacuum of space. Space is not a complete vacuum. I'm here in Ohio Stadium, home of the Buckeyes. It's very empty today. I'm the only one here, and can't think of a better place to illustrate the vacuum of space.
The empty stadium can be a stand-in for the vacuum of space if we compare it with what it looks like on game day. With more than 102,000 people in its seats, Ohio Stadium would be like the atmosphere on Earth, jam-packed with air molecules.
So how much do we have to clear out this stadium to equal the vacuum of space? Believe it or not, you have to clear out everybody, including me, and then even I'm too much.
No more than a single cell from Pogge's body could remain in Ohio Stadium to come close to the vacuum of deep space. With what seems like almost nothing in the expanse between galaxies of the Perseus cluster, the existence of sound waves seems all the more incredible.
How do you propagate a sound wave through empty space when it's mostly empty? Let's use the example of me running down the field. I have to run a long ways before I encounter somebody, but I still encounter somebody and I can pass energy along to them. The same is true of atoms in interstellar space. It has to travel a long ways, maybe 300 light years before it encounters another particle, but when it encounters it, it passes the energy and the wave moves along.
The colliding particles in the Perseus cluster also emit faint X-rays, whose traces, imaged by the Chandra Space Telescope, tell us the waves are there. But these waves are huge, and the notes they produce are lower than anything any human has ever experienced.
The pitch is about 57 octaves below our hearing, below the middle of a piano range, and that actually qualifies this for the Guinness Book of Records as the deepest pitch known to man.
The extreme deep note emanating from Perseus is so far below our hearing range that it can only be approximated. It's been said the galaxy cluster is playing an awesomely low B-flat, and scientists calculate it'll be playing constantly for 2.5 billion years. Number 9's deep tone of Perseus drones on as the countdown advances. A secret number 1 waits at the end of the line, but first, a strange high-pitched squeal hints at what comes in at number 8. Sounds from space and their link to signals from extraterrestrials. Starting with the Big Bang, we've been tracking the top 10 of the universe's greatest hits. The best of the alien sounds from space. Jumping to number 8 on the countdown, we find a sudden wide variety of different sounds. Clicks, whines, and screeches, all coming from strange stars singing out from everywhere we look in the galaxy. They're cosmic squeals with a rhythm section in the beat of the pulsars. Every pulsar has a different sound, but they are all related because they are repeating blips, beating out regular rhythms. The different sounds come from beats sounding out at different speeds. The first pulsars to be detected emitted radio waves so regular that astronomers first thought they were signals from aliens. But the truth about them was quickly discovered.
A pulsar is a rapidly rotating neutron star. That's a very dense star, and it's got 2 beams of radiation coming out the poles. As those beams rotate and intersect our line of sight, we see a series of pulses. We can think of pulsars being associated with sound because they were first discovered with radio telescopes. There was a series of beeps that radio telescopes detected. For a slowly rotating pulsar, you might have a series of beats like a metronome. Beep, 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 beep. Or you might hear a beep, 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 beep. Now for a rapidly rotating pulsar, the beeps blur together, so you get like that. And for a very rapidly rotating pulsar, it's just a continuous sound that registers like a note in your ears.
Pulsars form from the collapse of very massive stars after they explode as supernovas. But how long does it actually take for a massive star to collapse? That's what Sherman D. of Tampa, Florida wanted to ask the universe when he texted his question to us.
Sherman, the visible effects of a supernova can last for months or years or even centuries if you're looking at the supernova remnant, the expanding gases. But although it may seem incredible, The collapse of the core of a massive star can take just a second or two, and that's what initiates the supernova explosion.
Our own sun isn't massive enough to go supernova, but it is a giant ball of hydrogen, 330,000 times more massive than the Earth and burning by nuclear fusion. So our home star can hardly keep quiet, as our next hit proves. This hot combo chimes in at number 7 on the countdown. Here it is, the Song of the Sun.
The sun makes sounds, but they're not really sunny sounds. They're not happy sounds. They're kind of low, ominous roars that gurgle along. The sun makes sounds because there are a bunch of gases going up and down through a process called convection. So they're sending pressure waves through the ball of gas that is the sun, and it kind of rings like a bell.
Unlike a bell, the sun rings with 10 million different tones at once. We detect them from the tiny bulges from the pressure waves on the sun's surface. Solar satellites measure the height of the bulges with exquisite accuracy. Apart from sound, they also produce science.
So using these sounds from the sun that we can observe, we can actually tell very detailed things about the interior structure of our star. For example, one of the amazing things that we can tell is when there's a sunspot group on the other side of the star, even before it comes around the limb and we're able to see it with our optical telescopes.
The sun may be the biggest source for sound in the solar system, but next in line is Jupiter. So coming in at number 6 in the top 10 is a medley of strange electronic jazz from Jupiter. Jazz from Jupiter comes to us courtesy of the 2 legendary Voyager spacecraft, now on their epic journey to the edge of the solar system.
The 2 Voyager spacecraft are headed for interstellar space. They're on the very outer edges of the bubble the sun creates around itself. Today, Voyager 1 is 118 times as far from the sun as the Earth is, almost 4 times as far from the sun as Neptune is.
Project scientist Ed Stone has been heading the Voyager mission since its 2 spacecraft made their grand tour of the outer planets, beginning in 1979. On their approach to Jupiter, the first thing each one encountered was the giant planet's bow shock, producing a wind-like sound from the electronic data.
There's a wind blowing outward from the sun at about 1,000,000 miles per hour. It is supersonic. As that wind approaches contact with a magnetic field around, say, Jupiter, it has to go subsonic. There is a sonic shock which forms in front of the magnetic field of Jupiter. That's called the bow shock. It's very much like a sonic shock in front of a supersonic aircraft.
More intriguing than the bow shock is the Jovian chorus, sounding something like the chorus of birds chirping at dawn. Both it and the bow shock come from radio waves generated by fast-moving charged particles within the bubble of Jupiter's magnetic field. Now, the scramble toward the mysterious number 1 in the top 10 swings to the moons of Jupiter and the rings of Saturn, where the noises from electric loops, glowing gases, and streams of wind vie for distinction as the spookiest sounds in the solar system. The top 10 countdown in the alien sounds of the universe has reached Jupiter, sending out its own brand of space music. But the next hit is no solo. Jupiter has a backup group. They're the Jovian moons circling the giant planet. And now they have their own album. It places at number 5 in the top 10, and the tune is called Moons Over Jupiter. The lead singer is the moon Ganymede, recorded by the Galileo spacecraft, arriving at Jupiter in late 1995.
The sounds that Galileo sent back from Jupiter's moon Ganymede, by the way, the largest moon in the solar system, are very intriguing. They sound a little bit like an alien fax. In fact, when I played that sound clip in my office yesterday, people came around the corners to see what was going on, if I was receiving some alien transmission.
As with Voyager, Galileo's sounds came from ionized gas, or plasma. Atoms in a plasma are split apart into negative electrons and positive atomic nuclei. In other words, charged particles. 2 slender antennas on the spacecraft's plasma wave instrument picked up the radio waves that the charged particles produced as they were set in motion by a magnetic field.
These sounds that we hear from Ganymede are the evidence that Ganymede actually has a magnetic field. And you cannot find that information without using the plasma wave instrument, as we did on Galileo.
A very sudden burst of alien sound came from another of Jupiter's moons. It happened when Galileo flew over Io's North Pole.
My favorite moon in the solar system is Jupiter's moon Io. It looks a lot like a pizza. This is the most volcanically active moon in the entire solar system, 10 or 100 times more volcanically active than the Earth. It literally spews tons of material into space every second, sulfur and oxygen atoms. These get ionized in Jupiter's magnetic field and actually connect back to Jupiter, to the north and south poles, making a donut.
The donut is called the Io flux tube, and the charged particles carry a monster electric current between Jupiter and its volcanic moon. As Galileo flew through it, the sound ended as abruptly as it started. With Jupiter and its moons finishing their acts, our countdown swings to Saturn, smaller than Jupiter, but right up there in the top 10. The ringed planet comes in at number 4 on the list. Listen up for the surreal sounds of Saturn. They come to us from the Cassini spacecraft, which has been delivering mind-blowing pictures and data since its arrival at the ringed planet in 2004. As on Voyager and Galileo, Cassini's plasma wave instrument is our proxy for human ears in space.
The eerie and bizarre sounds we hear from Cassini's radio and plasma wave instrument make me think of Halloween. They're due to the aurora on Saturn, very similar to Earth's aurora. Your ears could never pick up these frequencies, but we move them into a range, and when we do, we were surprised to see how eerie and scary they actually were.
The surreal sounds of Saturn isn't the ringed planet's only song on the countdown. Turn it over and we find number 3 on the playlist, Saturn's Flip Side. Scientists call this hit a crossover. This crossover has nothing to do with mixing musical styles, but describes radio waves from Saturn's northern and southern hemispheres as they actually crisscross in frequency over a period of time.
We saw something really strange in our radio data, in our plasma wave data, a couple of crossing frequencies that apparently suggested that the northern and southern hemispheres were rotating at different rates. That's very unfamiliar to us on a solid Earth, where the Earth rotates at one rate. It actually turns out we don't think Saturn's rotating at different rates. We think that high altitude zonal winds are tricking us and making us think that there's different rotation in the northern and southern hemisphere, but it's probably not the case.
Similar waves following the lines of Saturn's magnetic field revealed a surprise about the ringed planet.
One of the most bizarre things that Cassini found was apparently the Saturn day was about 6 minutes longer than it was back in the days of Voyager, mere decades earlier. The determination of the length of Saturn's day is actually not possible by watching the clouds rotate around the planet. We have to use these radio emissions, the sounds of space, to see what the deep interior is doing. And that's where we found this mystery.
It's virtually impossible to slow down a planet the size of Saturn that much in such a short time. So scientists now realize the radio emissions probably don't give an accurate picture. And by sophisticated mapping of Saturn's winds, they now have a better take on Saturn's day, which happens to be 10 hours, 34 minutes, and 13 seconds long. Now we're close.